this session, I would like to focus my attention on the verification of data and removal of errors, if any. It is important to check the acquired data for errors due to possible inaccuracies, omissions and other factors. The errors in the spatial data are generally checked by printing the data or by taking its computer plot, preferably on a translucent or thin paper at the same scale as the original. The printout or computer plot is placed over the original map. The two maps are compared visually and the discrepancy in the form of missing data, locational errors and other errors are clearly marked out on the printout. Checking of the attribute data is also done by visual inspection of the printout. A better method of checking the attribute data is to scan the data files with a computer program that can locate the gross errors such as text instead of numbers, numbers exceeding a given range and so on. Errors may arise during the capturing of spatial and attribute data in the following cases. So, now let us look at what could be the errors in spatial data. These could be that the data is incomplete or double, or it is at the wrong place, or defined by using too many coordinate points, or it is at a wrong scale, or the data is distorted. So, let us look at them one by one. So, when the data is incomplete or double, when the data are entered manually, incompleteness in the spatial data may be due to omissions in the input of points, lines or cells. In case of scanned data, this error of omission is usually in the form of gaps between lines, where the raster to vector conversion process failed to join up all parts of a line. The raster vector conversion of scanned data can lead to the generation of unwanted spikes. Sometimes, one line may be digitized twice and lines and nodes may be disjointed at the intersection. Now, the data can be at the wrong place also. Spatial data may have minor displacement errors to gross spatial errors due to mislocation of spatial data. Minor placement errors are usually the result of careless digitization. Gross spatial errors are due to change of origin or scale that occurs during digitization or as a result of hardware or software faults. Similarly, spatial data may be defined by too many coordinate pairs. Well, this could be a result of both digitization and scanning process. Lines in the database may be defined using too many points, resulting in use of large storage space in a computer. This type of problem is generally experienced when the digitization process is in a continuous streaming mode, where the information may be acquired as per a certain communication speed, which is known as the baud rate. Now, if the person digitizing the information does not maintain a uniform speed of moving the cursor during the digitization process, there can be large number of similar values which may be entered into the database. So, this is a very common phenomena which may be coming when one is doing digitization on a digitizing table or a on screen digitization using a continuous stream mode. The next type of error could be that the spatial data is at the wrong scale. The digitization at the wrong scale results in erroneous representation of the spatial data. In case of scanned data, the problem usually arises during the georeferencing process using incorrect values. Similarly, the data may be distorted. Spatial data may be distorted if the base maps used for digitizing are not at the correct scale. Usually, aerial photographs do not have uniform scale over the whole of the image because of relief and tilt distortions and sometimes due to aberrations in the lens properties. Paper map may suffer from paper stretch, which is usually greater in one direction than another. In addition, paper maps and field documents may contain random distortions as a result of having been exposed to rain, sunshine, frequent folding, etc. Transformation from one coordinate system to another may also cause error in the spatial data. These errors are addressed through various editing and updating functions supported by most GIS software. Data editing is done usually by viewing the portion of the map containing the error on the computer monitor and connecting them through the software by using a mouse or a keyboard or a digitizer. Data scaling problems may be overcome by applying simple numerical factors to the data. More complex rotating and translating operations are needed when fitting various data sets together, such as a distorted thematic map to a accurate base map. The faulty map should be corrected with the base map and a number of points on the original map linked by vectors to their correct position, as shown in the figure, where T is the transformation vector. Mathematical transformations, stretches or compression of the original map until the linking vectors have shrunk to 0 length and the tie points are registered with each other. It is then assumed that all other points on the original map have been relocated correctly. This process is known as rubber sheeting or wrapping. This method cannot be applied directly on rasterized data because of the rigidity of the fixed grid and the structure of the data. Attribute values and spatial errors in raster data are corrected by changing the value of the faulty cells. We have discussed that a data can be at a wrong scale or it could be at a wrong place. This is primarily because of a lack of correlation between the input data and the data which has been created. In order to resolve this ambiguity, we need to georeference the GIS data. A spatial referencing system is required to handle spatial information. The primary aim of a reference system is to locate a feature on the Earth's surface or a 2D representation of this surface such as a map. A map portrays accurately worldwide features that occur on the curved surface of the Earth. The objective of a georeferencing is to provide a rigid spatial framework by which the positions of the real world features are measured, computed, recorded and analyzed in terms of length of a line, size of an area and shape of a feature. Several methods of georeferencing exist, all of which can be grouped into three categories as under: geographic coordinate system, rectangular coordinate system and non-coordinate system. So, let us look at them one by one. Geographic coordinate system. The geographic coordinate system is the only system that defines the true geographical coordinates in terms of latitude and longitude. The Earth is defined by a reference surface using latitude and longitude. As seen in the next figure, the lines of longitude, also known as meridians, start at one pole and radiate towards the other outwards until they converge at the opposite pole, while lines of latitudes lie at right angles to lines of longitude and run parallel to one another. In this particular slide, we can see the North Pole and the South Pole, and the circle which is joining these two is the longitude. At any point on the Earth's surface, the longitude of a place is referred to the Greenwich meridian, and this is the 0 longitude values. All places to the right of this particular meridian would be referenced as east, and all places referenced to the left would be designated as west. Similarly, the circle lying at the center of the sphere is the equator. This is the 0 latitude. All latitudes above this are referred to or designated as northern latitudes, and all latitudes below this are referred to as southern latitude. So, we can say that the Earth's surface can be split into various quadrants depending upon the location in which the place is located with respect to the two reference planes. One is the equator and the other is the Greenwich meridian. The next coordinate system is the rectangular coordinate system. Since most of the spatial data available for use in GIS exist in 2D form, a referencing system that uses rectangular coordinate is most suited. This requires a map graticule or grid placed on top of the map. The graticule is obtained by projecting the lines of latitude and longitude from our representation of the world as a globe onto a flat surface using a map projection. The function of map projection is to define the positions on the Earth's curved surface when transformed onto a flat map surface. There are several map projections and a variety of these are in common use, since no single projection can meet all the requirements of all the users. One of the most commonly used coordinate system is the universal transverse Mercator. It is the simplest regular square grid widely used for coordinate system of small areas. For larger areas, certain established cartographic projections such as universal transfer Mercator projection or UTM are commonly used. This projection uses multiple cylinders that touch the globe at 6 degrees of longitude, dividing the globe into 60 projection zones, avoiding the pole. This particular slide, as a matter of fact, shows us the manner in which the UTM projection system splits the earth into different layers or zones. The UTM projection has been adopted by many organizations for remote sensing, topographic mapping and natural resource inventory. Realizing that the UTM is the most popular coordinate system amongst map users, most of the digital products in United States of America are being produced on UTM projection. Recently, many GPS receivers are adopting this coordinate system as an option. In fact, making it a de facto standard coordinate system in the spatial data collection industry. The third type of coordinate system is a non-coordinate system. In a non-coordinate system, spatial referencing is done using descriptive codes rather than coordinates. Most widely used postal code, which is appended to a postal address, is one of the examples of georeferencing using codes. These codes may be completely numeric, such as 267667, which is a pin code in India, or alphanumeric code such as DL3 6KT, a postcode system adopted in United Kingdom. The basic purpose of such codes is to increase the efficiency of mail sorting and delivery rather than to be an effective spatial referencing system for GIS. This particular slide shows the two types of non-coordinate system, wherein in one only numeric codes have been used, while in the other alphanumeric codes have been used. The concentric circles show different types of activities, like the innermost circle is the delivery post office, which may have a number 267667. The next circle defines the sorting office route and may be designated as 2676. The next circle could define the subzone and the sorting district, and finally, the postal office zone, that is the one in a region, could be defined by a single alphanumeric code. Similarly, the alphanumeric codes may also be used for identifying the postcodes. Here, we may have different postal code sector codes, district codes and postal area codes, and each will have different types of representation. This system has the following advantages. First, provides coverage of all areas where people reside and work. Individual codes do not refer to a single address. Provides a degree of confidentiality for data released using this as a referencing system. Having had a look at the different types of coordinate systems, now let us look at what could be the spatial data errors which one may encounter. It is essential that the GIS products are high quality products, and this can be achieved by making use of quality data with minimum errors. The data to be used in a GIS may have some inherent errors, and some errors are produced by the system while working with the data. It is important for the GIS users to document the limitations of their source data and the subsequent output generated. The errors which one may encounter are the data quality and errors accuracy and precision, biasness, completeness, compatibility, consistency and applicability. So, data quality and errors. The term quality is used for describing problems and errors associated with the sources, propagation and management of error. Examining issues such as error, accuracy, precision and bias help in assessing the quality of data sets. So, let us look at what actually is errors, accuracy and precision. The errors in a data set refers to the faults, including the statistical concept of error, meaning variation. Accuracy is defined as the degree of conformity or closeness of a data value to its true value. An accurate GIS database represents the real world. On the other hand, precision is the degree of conformity or closeness of repeated observed values of the same quantity in the data sets to each other. To give a simpler explanation to accuracy and precision, let us consider the wristwatch that one may be wearing. Now, it could be that at a given time the clock may be either running ahead or behind. Well, we would say that the clock is, what should we say? Is the clock accurate or is the clock precise? Well, at this point of time we will say that the clock is inaccurate, because it is not showing the correct time at that particular instance. So, if it was 10 o'clock in the morning and the clock is showing 5 past 10, that means there is an error of 5 minutes in the wristwatch. But if we observe again on a number of days, that is again in the night, we find that when it is 10 o'clock in the night, the clock is still showing 5 past 10. Now, we will say that the clock is precise, even though it is inaccurate, but it is precise, because it shows repeated and similar trends in the representation of the inaccuracy which is there. So, this type of watch would be called as a precise, but inaccurate. I hope this makes these two terms very clear, because it has to be understood that a confusion between these two will have lot of impact in our subsequent GIS analysis procedure. It is perfectly feasible to have a GIS database that is highly accurate, but not very precise, and vice versa. Computers store data with a high level of precision, which does not imply that the data set is of a high level of accuracy. The next type of spatial error could be the bias. Bias in a GIS data indicates the systematic variation of data from reality and can be referred to as a consistent error throughout a data set. For example, a badly calibrated digitizer introduces a consistent overshoot in the digitized data set. The next is resolution. Resolution is an important concept when we are dealing with spatial data. It is dependent on the scale of the original map, the point size, the line width of the features representing thereon, and the precision of digitization. Next is completeness, compatibility, consistency and applicability. A GIS data set should be complete, spatial and temporally, including with respect to attribute information. Different data sets in GIS database should be compatible to produce a sensible result. Compatibility can be ensured using similar methods of data capture, storage manipulation and editing in producing ideal data sets. Consistency should be observed within individual data sets. Inconsistency may arise within a data set when different sections of a data set come from different sources or different people digitize them. Applicability or suitability of a data set is viewed in terms of a set of commands, operations or analysis. Now, let us look at some of the sources of errors which could be there. These errors in GIS database may be categorized as conceptual errors, source data errors, data encoding errors, data editing and conversion errors, data processing and analysis errors and data output errors. Conceptual errors. Conceptual errors arise from our understanding of the real world and how it is modeled. The perception of reality varies from person to person and this affects the data. Whatever GIS model is adopted, it is a simplification of the reality and thus any simplification will introduce errors of generalization, completeness and consistency. Source data errors. GIS spatial and attribute data collected from various sources are likely to include errors. The errors in survey data can be due to positional errors, instrumental errors and personal errors, whereas data collected by remote sensing and aerial photography may have the errors due to wrong spatial referencing and mistakes in classification and interpretation. The temporal changes in the features also introduce errors due to time and date of data acquisition. Maps, probably the most frequently used resources of data, contain errors in both spatial as well as attribute data caused by human or equipment failings. The cartographic process used in map making introduces suitable errors in maps. Next is data encoding errors. The process of transferring the data collected through maps, remote sensing or ground surveys into a GIS format is referred to as data encoding. Data encoding is probably the greatest source of error. Digitizing a map is one of the processes of data encoding in GIS. It can be done manually or automatically using suitable computer hardware. Despite the availability of hardware for automatic digitization. Most of the digitization work is done manually, involving human judgment and limitations, which is one of the main sources of errors in GIS. Translating a continuously curved line on a map onto a digital image involves a sampling procedure or process. Out of the infinite number of points on the line, a very small number of points along a curve are sampled due to human limitations. In this, what we can see is that the original line is a very smooth line, but as the digitization takes place, the cursor may not fall exactly over the original line, and there can be certain deflections from the original shape. There can be abrupt shaking of the human hand. So, different types of errors during digitization may take place. For example, undershoot, that is, we are not reaching to the desired position where the line exists, or there is a sudden peak which we call it a spike, or there could be a overshoot in the point where the cursor has been placed. So, we may have a dangling line. So, these are some of the typical errors which may come while the digitization process may be undertaken. The errors are also introduced due to incorrect registration of map document before the digitization commences, both in manual and automatic digitizing. Raster scanners used for automatic digitizing suffer from resolution problems. Next is editing and conversion errors. Since the data input by either manual or automatic digitizing is never without errors, it will almost always require editing and cleaning. It is difficult to locate errors precisely and remove them, but many of them can be removed by careful scrutiny of data. Figure shows some of the common errors in the digitizing and the effect of editing and cleaning using automated procedures available in some of the vector GIS. The tolerance limit set for cleaning the errors has its own effect on cleaning depending on its value. So, let us look at what could be the different type of editing and conversion errors. So, here on the left hand side, we find there is a polygon which has been digitized. So, what we find is while digitizing the polygon, at the topmost there is a gap. It is an unintentional gap, but it leaves the polygon unclosed. The same thing happens at the other end. There can also be an additional line which could be there, which may have been created. Similarly, what we can do is by applying certain techniques, we can remove these errors. When we apply these errors, what may happen is we may provide a small tolerance limit. This would, as a matter of fact, allow the closure of some of the points, but some of the points may be left open. Similarly, if the tolerance limit is too large, it could be possible that some of the small polygons may be removed. While dealing with a raster GIS, a different problem arises when using the automated techniques for cleaning. In raster GIS, the noise, also referred to as misclassification of cells, can be either regular, for which is easier to identify, or scattered randomly, in which case it is difficult to locate. The noise errors are rectified by employing filters which reclassify single cells or groups of cells by matching them with general trends in the data. It is important to choose an appropriate filtering method, as the wrong method may remove genuine variations in the data or retain too much of the noise. Then spatial data errors. After cleaning and editing the data, it is required to convert the vector data to raster data or vice versa. When raster data is converted into vector, topological ambiguities, as can be seen in the next figure, are introduced. When converting vector data into raster data, both size of the raster cell and the method of rasterization used have important implications for positional errors and in some cases attribute uncertainty. So, first of all, let us look at a conversion of from vector to raster information. We can see in the original vector map we have two polygons A and B. When the vector is converted into a raster, what we find is that instead of two polygons A and B, now we are having three polygons A, B and C, where B and C are basically the same polygon in the vector map, but primarily because of the cell resolution of the raster GIS, it has undergone a breakpoint, and what we find is instead of two polygons A and B, now we are having three polygons A and B, and this is due to the pixel size that has been selected, which implies that the analyst must be conversant that depending on the type of the shape of vectors which are there, the appropriate raster cell resolutions must be defined, or else these type of typical problems may be encountered frequently. Positional and attribute errors resulting from generalization are found as classification errors in cell along the vector polygon boundary, that is stepped appearance in the raster version when compared to the original vector form. Besides topological errors, conversion from vector to raster may lead to loss of small polygons and different raster maps due to inaccurate placement of grids for rasterization in respect to orientation and origin. Then we may have processing and error analysis. Before processing and analysis of GIS data are undertaken, the user must ensure the following. First, the data are suitable and relevant for analysis. The data sets are compatible. The technique to be employed is appropriate. GIS data processes that can introduce errors are mainly classification of data, aggregation or disaggregation of area data, and data integration by overlay techniques. A common error arising due to overlaying two polygon maps is slivers. These are very small polygons along correlated or shared boundaries of two input maps. This particular figure shows the effect of slivers. We have an original forest map, and this has been digitized at a particular time t1. The same polygon has been digitized by at a different time t2, and what we find is that these two polygons, when they are overlaid, they do not match. There are some areas of mismatch, either there is an extra area outside or there is an area which has been cut out by the two polygons which have been created. So, this is a very common problem that is present when we have to overlay two different data sets coming from two different sources or collected at two different time frames. Next is data output errors. Due to inaccuracies of the GIS database and the errors resulting in manipulation and analysis of data, it is inevitable that all GIS outputs, whether in the form of paper maps or digital database, will have discrepancies. The extent depending on the attention and care taken at all stages, starting from construction, manipulation and analysis of GIS database. In my next session, I will focus my attention on GIS data models by which data can be stored in a GIS environment. Thank you.